Bhagat sir, shall we start? Are you?
Yeah, I'm always ready. But the number of participants are very less. सिर्फ 15 दिख रहे हैं मुझे. 2 मिनट रुकते सर, स्टार्टिंग में ही बेसिक्स क्लियर हो जाता है, बाद में फिर उन लोग ऐसे ही बैठेंगे. मतलब 5 मिनट तो रुकते.
ओके, ठीक है, ठीक.
स्टार्टिंग मिस किया तो फिर 5 मिनट.
ठीक है, जब चालू करना है ना हाँ ठीक है, ठीक है. जब आप बता दीजिएगा मनीषा मैडम ठीक है. 5 मिनट के बाद चालू कर दो. 5. ओके ठीक है. ओके.
मनोज सर नमस्कार. भगत सर बोलतोय.
हाँ सर, नमस्कार सर.
कसे आहात?
फर्स्ट क्लास सर एकदम.
गुड टू सी यू.
यस सर. सेम टू यू सर.
थैंक यू. राठौड़ सर शुरू करते हैं. कुछ नंबर बढ़ तो नहीं रहा तो मनीषा मैम.
Yes, sir. Good afternoon, everyone. So, Manisha Bansure welcomes you all to sponsored STTP on VLSM design using cadence tools. It is a great pleasure for me to introduce our speaker for today's afternoon session, Narendra Bhagat sir. Professor Narendra Bhagat is Associate Professor in Electronics Engineering. Plus 20 years of teaching experience. His area of interest is digital circuits, logic circuits, circuit VLSI design, and current mode circuits. Sir, I request to join today's session.
Thank you very much, madam. Let's read my screen, sir.
No, you just share. I have given you the access rights.
Okay, shall I share my screen now? Hello?
Yeah.
And sir, one more thing. Am I properly audible?
Yes.
Just need a feedback. Am I properly audible? Okay. I'll do one thing. I'll share my screen. Visible?
Yes.
Okay. So shall I start?
Everything fine. Yeah. Go ahead.
Okay, I'll go ahead. But in between, if any participant feels or video is not coming properly, please immediately unmute yourself and give me the feedback. Few instructions before I start. While the presentation is going on, I request all of you to mute yourself. If you have any doubt, you can jot down the slide number, and at the end of the session, you can ask me the questions. Of course, in between, if you feel that no, it's very urgent question or you need to ask that time itself, you can definitely unmute yourself and ask the question. But preferably during the whole session, I request everybody to mute yourself. I'll be going very slow, assuming that you people don't know anything about the analog VLSI as such. But definitely as a electronics or electronics telecommunication teacher, the prerequisite is you should be knowing a bit of circuit theory, that is basic KVL, KCM, Kirchhoff's voltage law, Kirchhoff's current law, that is nodal and mesh analysis. Other small prerequisite is you should be knowing a bit about the linear integrated circuits. That is how the operational amplifier works, or I would say how the oscillators are designed, etc. The basics of LICD, that is linear integrated circuits, and circuit theory is, I would say, must, not 100%, very little bit is required. So start my session. The title of my topic is implementation of communication circuits using current mode technique. Now, if you see the number of slides, don't get afraid. There are 120. So at the start, I'll be going slow. It's definitely 2-hour session. Maybe in 1.5 hours, we can finish. Now, during online mode, sometimes it depends. Sometimes it goes very fast. Sometimes it may take time. If the interaction is there, definitely it takes actually more time. But as I said, if you have any urgent doubt, you can ask in between. Before starting the session, I would just give you brief introduction without going to the next slide. So what exactly is current mode technique? So before going to the slides itself, let me tell you, in market right now, the techniques or the devices which are available are majorly voltage mode. So what do you mean by voltage mode? The input is a voltage. The output is also majorly voltage. Sometimes it can be current also. Simple example like operational amplifier, op-amp. The one which teach to our students like IC741 or LM675. So there, majority of the time your input is voltage, output is maybe voltage or current. Of course, we have sometimes voltage to current converter. But what do you mean by voltage mode is that device will have voltage as input and majorly voltage as output. So the disadvantage of that is, taking an example of operational amplifier, as voltage is given as a signal, and if you're giving a digital signal, you need to give logic 0 and logic 1. So the supply voltage requirement for voltage mode is generally high, more than maybe 2 volts. Previously, we used to talk about 5 volts, but nowadays we can go lower to up to 2 volts. Here, what I'm proposing, of course, that's the area of research where we have something called as current mode technique. Now, in current mode technique, the input is current, output is again majorly current, but of course, by using a grounded resistance, we can have voltage also. So that's how we differentiate. Voltage mode circuits में input voltage, output voltage. Current mode circuits में we have current as input, output is also majorly current, sometimes voltage also. The advantage of this is, as I have given the example, if you have a digital circuit, then logic 0 current se dena hai. So I can give few microamperes as logic 0 and few milliamperes as logic 1. As the signals are in very low current, the supply voltage requirement is very less. Around maybe 1.2 volts is sufficient. Some of the literatures have also gone less up to 0.5 volts also. And of course, they are working in sub-threshold region. So the major advantage, as your supply voltage requirement is less, the power consumption is also less. So using this current mode technique, I have tried to implement few communication circuits in my research. So now I'll be going ahead. So that part will be repeated majorly because the major aspect here is what do you mean by current mode? What are the advantages of current mode over the voltage mode? And when we want to design few circuits, what exactly is the aspect of that? Okay, so I'll be going ahead with the next slide. Content in brief, first introduction, then outline where I'll be covering basics. Then these are the different, I would say, checkpoints or the work which we have done. Current mode versus voltage mode. This third point is very important, guys, where what we will be learning is something called as adjoint principle. I'll talk about it later because abhi bol ke matlab nahi hai, so I'll be covering that one by one. Then what we have done is a verification of voltage mode and current mode at circuit level. When we found the success in that, then only we went for something called a CFOA design, that is current feedback operational amplifier. So after designing our own CFOA, which is actually inspired by a commercial IC called as 8844, we have checked that CFOA design for various aspects. After testing and it is found that it was working fine, we have checked it as an inverting amplifier for the gain of minus RF by R1 by weighing the values of RF and R1. The content continues. Then using the same, we have designed FSK transmitter at both voltage mode, current mode. In the same, we have also checked that the same CFOA by using a novel technique called as current injection or current biasing technique, which increases its gain as well as minus 3 dB bandwidth. Then coming to the next, as we have made a transmitter, then we required a receiver for the communication. The major first part for that was band pass filters. So we have different designed different band pass filter for different frequencies using two basic filters. One is silent key and other is the advanced silent key filter. As we were using the current receiver, because the CFOA was used as in current mode also, so we required current rectifier circuit. So I'll come to that. Current rectifier was specifically designed. And finally, we have designed the complete FSK receiver using the commercial IC 8844 in both voltage mode, current mode, as well as the complete FSK receiver was designed using our own CFOA in voltage mode and current mode, and it was compared for majorly power dissipation. So this is today's whole content. I'll be going very slow at the start for making you understand regarding the advantages and the concept of current mode, why current mode to be used. So going ahead with the next slide. Introduction. This is all already what I have said, that there are challenges. We have the bottleneck of memory, power consumption, bandwidth enhancement. Already there are large number of voltage mode building blocks like operational amplifiers are available, that is cited. As compared to voltage mode building blocks, the current mode building blocks can be generally operated with low voltages and have higher bandwidth and slew rate, as I've already mentioned, and this will come again and again because we need to prove that ये कौन से basis पे हम लोग बोल रहे हैं. So we'll be covering. I'll be covering that also. In CM building block, as I already said, it is controlled by the input current. Due to the availability of the CM building blocks, the synthesis of analog circuit using these building blocks have received attention. Now, let me tell you, all the participants, that research has been going on since 1978. Scientists like Smith and etc., they have actually introduced the current mode building block called as current conveyors right from 78. And lots of debate is going on whether current mode is better or voltage mode is better. Right now, the market, or I would say the research community, have come up with different current mode filters, PLL, etc. blocks, so that now in market they are trying to replace voltage mode devices using current modes. So as I said, this is not a latest topic. Old topic is there, but the success is now, I would say, being gained. So before I go to the next, as I said, the current conveyors are the building blocks, and there are different generations of current conveyors, starting from current conveyors 1, 2, plus, minus, etc. As on today, the devices which are used and available in the market uses VM technique, and the advantages of the CM techniques are not yet explored. But as I said just now, that market has started accepting the current mode circuits because of the advantages. Justification of the topic, I have already cleared that, but still I'll go through this. So we are going to have low voltage supply and power dissipation and bandwidth increase will be there. That covers in the first 2 points. They will have a simple design because here we will be majorly dealing with nodal KCL. We'll be summing up the currents and going ahead for simple topologies. The recent work is going on in the CM technique, as I said, at various circuit blocks in communication such as filters, mixers, phase lock loops, sample and hold circuit, etc. Current mode devices are the ones where output voltage and or current are controlled by the input current. The reason to use current mode as they can have following advantages: operates with low voltages, higher bandwidth, provides high slew rate, and leads to simple circuit topology. So few things I have repeated here so that you'll understand why we are going for the current mode techniques. So what we have done is we have simulated latest circuit which uses the voltage mode technology and their performance characteristics. The same circuits have been implemented using the current mode circuits and compared the characteristics, compared the performance parameters. And the comparative study from my research point of view was mainly on power saving and bandwidth enhancement point of view. So one of the kind of derivation given in the literature, if you observe in this figure 1, left hand side we have a conventional op-amp in inverting amplifier configuration. Inverting amplifier configuration, we have the gain as minus RF by RG. And after doing the simple derivation in terms of gain and bandwidth, if you observe the last expression, bandwidth and gain product, if you see the last, I would say the last expression here to the left, bandwidth into gain is a constant that is A0 into F0. So as we must have learned or taught to our students that in operational amplifier, the gain bandwidth product is constant. So as the gain bandwidth product is constant, if you try to increase the gain, bandwidth reduces and vice versa. Unlikely, you have a general, I would say, model of a CFA taken here, current feedback amplifier. So similar derivation, if we do here, what happens is that bandwidth expression, you get something like this, where the value of Rx is assumed to be very small. So if you neglect that value, we get this kind of expression where we can say that, not ideally, practically, that bandwidth is independent of the gain. Of course, in ideal scenario, you take Rx as 0. Rx 0 lenge to gain ka component gayab ho jayega. So because of that, we can say ideally bandwidth is independent of the gain. But practically Rx value is never 0. It is some small finite value. So therefore, we can at least say that unlike operational amplifier, in CFA, we can say that bandwidth and gain both can be independently controlled. And from the expression in detail, it can be seen that there is a feedback resistance RF. So this feedback resistance RF controls the bandwidth, and the input resistance RG actually controls the gain. And we have actually proved this in the circuit level as well as device level. I'll go ahead. Before I start with the actual, I would say, my work explanation, let's have brief introduction or brief revision. Excuse me. So what we need to know, as I said, we require to have some prerequisite of circuit theory, some prerequisite of linear integrated circuit, as well as we need to know basic concept of MOSFET, how a MOSFET works. So that's why a quick recap, or I would say maybe revision. Those who don't know the MOS working at all, at least you should be able to follow these few slides. So what we have is a MOS transistor. We need to know its DC characteristics, that is VDS versus ID as well as VGS versus ID. Few important formulas majorly for drain current and the basic analog building blocks which are required for the current mode. I'll go ahead with the outline. This is a very important slide. I assume again that we should be knowing that what you can see on the screen is the current voltage equation for N-channel MOSFET. Guys, I'll just introduce you this in brief. If ID we call that the MOSFET is cut off. That means there is no channel form because your VGS is less than VT. So as your VGS is less than VT, that means your gate to source voltage is less than the threshold. So channel is not formed, your device is in cutoff. So that's very simple. The second is linear region. The condition for linear is VGS is greater than or equal to VT, and a drain to source voltage, that is VDS, is less than VGS minus V. And there's an equation of ID linear, that is half mu n C naught x W by L into bracket twice of VGS minus VT into bracket VDS minus VDS the whole square. But for us, what is important is the third equation, ID saturation. Of course, for the second equation of ID linear, if we go in the, I would say, near to cutoff, we call this also as a deep triode region. So basically, we say that when the NMOSFET is working in linear region, it acts as a resistor, voltage control resistor. Of course, basically, again, that is in very much near to zero, or that is also in analog terminology is called as deep triode region. For us, the most important equation is the third equation, that is the ID saturation equation. The condition is VGS is greater than VT, that means the channel is there, and VDS is greater than or equal to VGS minus VT. This is very important. If you substitute VDS in the second equation itself, you get the third equation. The only thing is that I have added that short channel effect also, that is 1 plus lambda times VDS. Majority of the time when the derivation is done, we neglect this, or we will neglect for convenience. So the whole discussion of wherever derivation comes in this research of mine, I would be using this third equation for ID saturation. Right now itself you can see that अगर मैं VGS minus V2 को एक side में ले लूँ, so यहाँ पे root of ID sat, okay, the other terms will go to that, etc., etc. So for us, we will make saturation current, because whenever I'll be using my circuits or MOSFETs for working, I would like them to work as a current mirror majorly. And in analog, in digital, we majorly talk about linear. Analog mein majority of applications we want our MOSFETs to work in saturation region, so that we can get that gain concept and the voltage swing. Anyway, so I'll go. We'll have in N ki jagah pe P channel MOSFET is as per convenience. Few books does it ulta, that is, they instead of calling VGS they call it as VSG. I would prefer to do only one change, instead of greater than, write less than, and vice versa. So just remember, if you want to remember the P channel MOSFET equation, wherever there is greater than, do less than and go ahead. Of course, the suffix will be replaced by P. So before going ahead, again I repeat, we are majorly interested in saturation equation. Majorly all equations or the derivation which I have used for design purpose uses this, and most of the time I have neglected 1 plus lambda VDS. With the same outline, or I would say prerequisite. This is the MOSFET transistor already in last 2 days, where ID is GMVG conductance. This is the linear region. Second one, if you observe in the first diagram, is clearly mentioned in the last line of the first. We have a voltage controlled resistor. It acts as a resistance. And in saturation region, we have the voltage control CCS. Of course, इतना easy नहीं है, इसमें भी बहुत सारे complications आते हैं. We'll see that. Yeah. So this particular part, highlighting the green one here in this near to zero, is called as linear region. Actually, it's also called as a deep triode region. It is acting as a voltage controlled resistor. And if you observe this part, particular blue graph ka arrow here, this is called as saturation region, where the MOSFET actually acts as a voltage controlled current source. It काफी है for MOSFET. One important part, because as I said earlier, the majority of the time you want to replicate the current. So this is the circuit. To your left, we can reference current. The condition for of I1 equal to Iref is both the transistors should be ideal and they should have same VDS as well as VGS. So therefore, if all the parameters here comes to be same, your I1 will be same as I reference. Of course, if you want I1 multiples of I reference, then you can adjust that by ratio of W1 and WR. Generally, हम लोग length बात नहीं लगाते. Generally, never. So length will always be assumed to be constant. So this is basic current mirror circuit. Or in my research, I have also used the cascode mirrors for better swing, noise immunity, etc. I'll go ahead. So just recap, by chance those who have joined in late, what I'm doing here, a recap of that. Current mode circuits have found increasing applications in telecommunication systems, etc. In current mode approach, the data is represented in terms of the branch current of the circuit instead of the node voltages, as in voltage mode circuits. The current mode devices are the ones where output is voltage and or current, but controlled by the input current. The simplest and the mostly used current mode circuits are the current conveyors. So basically what I have done, already existing current conveyors, I have modified or added buffer into that, or modified it as a CFO, a current feedback operational amplifier, as we have to have that extra node for giving the feedback. And then that CFO I have used as a building block to design transmit receiver, that is the communication block. Finally, with the help of current mirror circuits, the signals in the form of current could be replicated without difficulty. So all the prerequisite is over. Now I will be showcasing the work which I have done. Sorry. Okay. This slide is again a slight repeat, but major advantage whenever people ask why current mode. So current mode already proved by the derivation, gain and bandwidth are independent of each other. So they both can be varied simultaneously. Actually, they have to be controlled using RG and RF separately. In voltage mode, that is your conventional op-amp, the product of gain and bandwidth is constant. Therefore, only gain or bandwidth can be increased at the same time. So this is a repeat of that. Yes, now it takes some time because this slide explains the adjoint principle. One basic question to the participant: the way in circuit we have a concept of duality. What do you mean by duality? Voltage replaced by current, current replaced by voltage, inductor by capacitor, open circuit by short circuit, Thevenin's by Norton's, etc. Similarly, we also have in circuit theory a concept of reciprocity. So here one interesting rule which is obeyed by the voltage feedback amplifier and current feedback amplifier. I would like to highlight on that. Guys, if you observe on left hand side, you have a normal voltage feedback amplifier. What you see here is an inverting amplifier. So if you have an inverting amplifier, what would be the gain? Minus RF by RI. I will take it as R1 both sides. So I'll take it as R1. जैसे हम लोग normally रखते हैं, RI रखा तो भी चलेगा. RI is input impedance. So here left hand side is the circuit which you have already seen so many times, right? It is the gain V out by V in is minus RF by RI. Now what happens if this particular block is a voltage feedback amplifier, and if you are going to replace it, see the idea behind it. What I have done, मैंने तीन चीजें, listen carefully. I have just reversed the, it's like a mirror image. तो ये जो triangle है ना, यहाँ पे आप लोग देखोगे properly. So I have just reversed the triangle, right? Minus plus remains the same. If you observe, F and R1 positions are exactly the same, no change at all. But this VFA, this is a CFA, current feedback amplifier. The other second change, V out is been replaced by I in. So जहाँ पे output था, वहाँ पे मैंने input डाला है और input का दूसरा terminal ground किया. Wherever you have VI, that is input, input has been removed and that is grounded. And surprisingly, you will not believe, if I derive the relation of I out by I in, that is current gain it also gives you the same expression minus RF by R1. I hope guys you're getting it. Somebody can give me the feedback here, please. I repeat, 3 changes. I have done a mirror image of the circuit, but this was voltage feedback amplifier. This was replaced by current feedback. RF R1 position doesn't change. They remain exactly as it is. Vout replaced by I in, grounded as other input, and the Vi removed, and that particular terminal is grounded. And of course, this is coming from the literature from Texas. And if you check the gain, voltage gain expression, current gain, both are exactly the same. That is minus RF by R1. Shall I go ahead? Okay, so I assume that this is understood. Slide number 18. Yeah, somebody was speaking something.
Yes, sir. You can see the chat box, no? Bhagat, sir.
One. नहीं मेरा यहाँ पे ना one. Sanjay, yeah, somebody said yes, but how do I see chat box? Bigger
top
one.
Top में वहाँ पे लिखा हुआ chat. You just see at the top.
Go to the right.
Yeah.
I can see right now only 4 people on my screen. Show grid view.
No.
Show active speaker and thumbnail windows, or show active speaker window. Just give me a moment. I think I should go to drop down. No. 1 minute. See, right now on the right top, I can see show active speaker window video.
No, Bhagat, sir.
Sir.
So that you will have a top ribbon kind of thing, share, etc., mentioned.
Yes, yeah. Now I saw.
There is it, sir. You open it and you just expand it little bit, okay, and put it right hand side.
Yes. I'll just put it to the right hand side so that if anybody wants to chat. Yeah. So there are 3 yes, so I assume that people have understood. So I'll go ahead.
You can see from first comment. Continue.
Is Indrajit Singh Danjal is the first one to comment? Because I can see only 3 right now.
Okay, it's okay.
Okay, that's fine. Okay, so I'll go ahead.
Yes, sir, go ahead.
This slide, it is very important as such because majority of the time what I have done, when I say voltage mode, I have done the left hand side wala architecture. Whenever I say I want to do now in, I have taken either a ready-made CFA or CFOA or my own made, and I have used the adjoint principle everywhere, in starting from first circuit to the last circuit, and it perfectly works fine. And I can show you that also. So I'll go ahead with the next testing start. So what I have done, once we have decided ki yes boss, this is what we have to do, first let's why not check it on commercially available circuits like ready-made voltage mode and current mode, I would say CFOA and VFOA. So what we have done comparison of voltage mode and current mode for gain and bandwidth dependency. We have verified that in voltage mode, if the gain increases, bandwidth decreases, and vice versa. But in case of current mode, they can be controlled independently. In an amplifier, the resistance RF controls the bandwidth. I repeat, RF controls the bandwidth and RF controls the gain. And this is given, I would say this is inspired from the literature by Texas. I can click here and show. Anyway, I'll be sharing you this. So I'll go ahead and show you the results of this. So this is LM675, which is a commercially available operational amplifier. What I have done, I have implemented this in P.S.P.I.T, taking the model file, and this is a normal inverting amplifier. 1 minute. Yeah, this is normal inverting amplifier, and I have plotted the result 2 ways. First thing, here, if you observe the result, RF has been kept constant. So RF actually controls the bandwidth and RG controls the gain. But this is LM675, which is a voltage mode amplifier. So if you clearly observe, the gain and bandwidth are inversely proportional. If you observe the blue line, which is a gain, so as the gain, blue line is gain, yeah. So blue line is the gain. As gain decreases, your red color or orange color, the bandwidth increases. So it clearly shows that in LM675, which is voltage mode amplifier, the gain bandwidth is constant. But using adjoint principle, what I've done in the next case, I've used a 8844, which is commercially available CFA or CFO, CFA, sir, not CFOA. So if you observe, I've used that adjoint principle, mirror image, rest everything same, and after doing the simulation in P-Spice, surprisingly, if you observe, RF is 100, RG has been varied in like in the similar case of LM675 from 0 to 60 in the steps of 10. What you observe that gain reduce ho raha hai, gain is reducing, yes, but boss, the bandwidth is remaining almost constant. So it that in CFA 8844 RF से मैं क्या कंट्रोल कर सकता हूँ? I can control the bandwidth. Of course RG से मैं गेन को वेरी कर सकता हूँ, बट अगर मैं RF को कांस्टेंट रखता हूँ तो मेरा बैंडविड्थ चेंज होता नहीं है, which unlikely if you previous case. I repeat again, I'm going back. यहाँ the same thing, the RG changed from 0 to 30, 25 impact in the steps of 5. RF is kept constant, but gain bandwidth is, I would say, inversely proportional. Unlikely your bandwidth doesn't change. Similar, I would say, permutation combination is done with LM675. Now what I have done, I have kept RG constant and RF is varied from 0 to 600 ohms in steps of 100. Here if you observe that nothing is actually, again, sorry, they are again inversely proportional. Gain बढ़ रहा है तो bandwidth कम हो रहा है, but the variation is more. Comparatively, if I go with now 8844, guys, if you observe, यहाँ पे of course gain constant नहीं रह रहा है, but if you observe the gain column, gain का variation भी बहुत ज़्यादा नहीं है. It is varying from 1.5 to almost 3. So comparatively in 8844 and comparing 8844 and LM675, one conclusion was there with us that in CFA, the gain and bandwidth can be independently controlled, unlike in LM675, which is a voltage feedback amplifier. Once we got that confidence that the hypothesis which we have read कि current mode में ऐसा होता है, we were sure that yes, this is happening. Then we went ahead positively for designing our own CFO. So I'll go ahead. So as I said, there are already existing current conveyors. Sorry, you can see what I'm showing on the screen is CC2 plus, that is generation current conveyor, where you have X and Y as input and Z is the output. Depending on Z, whether it is coming inside or outside, we call it as plus or minus. There's a relation matrix given down. If you solve that matrix, you clearly get Iy equal to 0. You get X equal to Vy plus Ix into Rx. We say Rx input resistance is 0. And you get a very important relation that Vx is always equal to Vy. And last but not the least, you have something called as Iz equal to Ix. So this is just a block diagram, but if you observe the literature, as you have to satisfy these equations, in you always have either BJT or MOSFET. Starting research was done using BJT, but majority of the time you translate. Okay, so starting research was done using BJTs, but whether it was done by using BJTs or MOSFET, two things were common. That one, they used to always have something called translinear loop, and secondly, the current mirrors ka what do you say, packages kind of thing, or at least a pair of current mirrors. So this is our contribution. We have designed a CFOA where we have taken one buffer terminal also, that is W, for taking the feedback. So from the matrix, you can see the relations. Vx equal to Vy, Iy equal to 0, Ix equal to Iz, that is input current is same as output current, and also Vw is equal to Vz. So feedback can be taken either from Vw or Vz, but generally we have used Vw for the feedback, not to have overloading. or loading effect, sorry. So this was the conventional AD844. So as I said, or as shown previously, the simulation done using the AD844, which is actually commercially available IC. Again, today also it is popularly used for many applications. So this is the schematic using BJT, where majorly you can see the translinear loops and the current mirrors. So going through one literature cited as seen, they have used similar kind of concept and made a CC2. What we have done using this particular CC2 and the original AD844 BJT structure, we use the equations, design them, and right hand side, what you can see in figure 10b is the CFOA, current feedback operational amplifier, proposed by us. We have tested it for all the matrix equation which you have seen above. These are the, I would say, MOSFETs and W/L ratios. Here in this literature, whatever I'm showing, I have used 180 nanometer technology. Of course, after that, we have tried for 90 and 45 nanometer as well. Right now, whatever I'm showing is something which is the result which are published or almost going to get published. So I'm showing you those particular, I would say, research data. So now, guys, this is my, I would say, heart of the research I can say, or my work, which is a CFOA, current feedback operational amplifier. Everywhere after this, I'll be using. I've used this CFOA as a basic building block and basic concept of linear integrated circuit. We have seen like phase shift oscillator or frequency shift keying circuit, etc., etc. Going ahead. So there's a bit slight derivation. Of course, I don't want to go through this right now in detail. So I'll just read out a few things, what exactly we have. So there are basic 12 transistors. 14 transistors, sorry. Out of that 14 transistors 5, 6, 7, 8 are working as for the intention of increasing bandwidth. Here, basically, there are two current mirrors which can duplicate the current in the node X onto the node Z. There is also a property that the transistor M1, M2, M3, M4, the last pair, they are mixed translinear loop. I had shown some basic equations. So, if you go through normal, I would say, nodal or I would say mesh analysis, there is a simple voltage divider rule. Vxy is taken as VGS3 minus VGS4P. And after substituting the values of VGS from the saturation wala equation, the third equation was there where we had ID square. So using that, if you go through that, of course, I have to reduce the derivation here, not shown the complete one. What I would like to show you as a final result is on the next page. Finally, what is that we want is the expression of Rx, assuming that the mobility of PMOS and NMOS is same, which is actually not. But if you balance that for the derivation purpose, what we get is the expression of Rx. This Rx expression is very important for us for the next part, where we get is that 1 upon root of 8 C0 x W mu or W/L into I0. Of course, for getting this derivation, you have to refer the book Behzad Razavi, which actually makes your idea clear in understanding the data and how to take, I would say, intuitive results and approximations. So after substituting from the data sheet the value of mu C0 x, that is 12,000 mu, I0 what I have taken as 120 microampere, W/L ratio as given. What I found for my CFOA, the value of Rx is approximately 50 ohms, which is exactly similar to the commercial available IC AD844. I'm going ahead. So my CFOA has been designed, tested also. After testing, testing in the sense I have only tested it for the normal, equations for the matrix. After that, I tested it for, let's check whether it is acting as an inverting amplifier or not. So what I've done, I've taken my own CFOA with X, Y, Z terminal, Y terminal ground kiya. X terminal is kind of a negative terminal. I've given RI there. There's a feedback coming from RF. And after doing this, I would say I've got the result that the theoretical gain, which has to be up to 20 log of whatever we have, 20 log of 5, that should be 13.97. With the bandwidth of 106.2 megahertz, which is definitely higher than 65 megahertz, which is more than 8844. So I was getting approximately similar result. So I tested the same CFOA for different values of gain. So if you observe the previous one was for 5, so I've tested it for gain of 2, that is 20 log of 2, then 20 log of 5, 20 log of 6, etc. And I was approximately getting the similar kind of gain, but the bandwidth was increasing. So again, we could quite say that, okay, our CFO is giving us better results or kind of desired result. So then it, I would say, encouraged us to start making the block diagrams for the communication. So we've decided to use I would say, implement FSK transmitter. So we have used a simple concept using 2 phase shift oscillator, one for high frequency, one for low frequency. The clock was given after the output of the phase shift oscillator and collected at the resistor in the form of current. So it was current mode FSK. After the clocks given to the MOSFETs were inverted. So when one phase shift oscillator square wave or sorry, not square wave, sine wave is going, the other is stopped and vice versa. So internal diagram using the so-called adjoint principle. Those who are teachers and taught phase shift oscillator can agree that this is a phase shift oscillator, but this is not in voltage mode. This is in current mode technique using the adjoint principle. So you get the desired result. You may be surprised कि मैं current mode का दिखा रहा हूँ, पहले voltage mode नहीं दिखाया. So somehow 8844 didn't give me the desired phase shift oscillator result. It was giving lots of noise, so I used a different concept there. But my own design CFOA using adjoint principle and phase shift oscillator, I got the result of the FSK transmitter. So the upper waveform is the gate voltage given to the MOSFET. So for logic 0, I was getting high frequency, that was 33.3 kilohertz. For low frequency, that is logic 1, I was getting 3 kilohertz. The power consumption which comes from the net files are given. Also, I've tested for different values. Here, I have used a simple formula 1 upon 2 pi root of LC of the phase shift oscillator and got one more result. The logic 0 here is 1 megahertz, which is quite dark or thick on the left hand side. If you zoom it, you get the same result. Logic 1 is 3 kilohertz. So this was FSK transmitter using CFOA current mode. For different 2 cases I have shown here. As I just said that somehow, unfortunately, the voltage mode was not possible to implement, or the 8844 didn't work there to work as a so-called sorry, not 8844. Yeah, 8844 doesn't supported us as a voltage mode. I was not getting using phase shift oscillator. So we have used the concept of ring oscillator. So using 3 back-to-back 8844 as inverter, we have used and got the voltage mode. So these are the voltage mode output waveforms for logic 1 and logic 0. The power consumption is definitely high here because the circuit was bigger for logic for 2 different reasons. I made sure that I use the same frequencies for logic 1 and logic 0 in both the cases. So friends, up to this, what is being shown is a transmitter. And there's a comparison of FSK transmitter in voltage mode and current mode. Here the comparison is not to the best because in current mode I have used CFOA and the technique was phase shift oscillator, and in voltage mode it was definitely ring oscillator. The comparison actually cannot be done here, but I have definitely made sure that it is possible to do it in the receiver side. Excuse me. Yeah. Now, Guys, are you there with me? I think one doubt here. Sir, are the resistor values of CFA are in ohms? Yes, yes. Good doubt, Inderjit. Sir, when you are working with the op amps in voltage mode, I'll just answer that because he has asked the question. This one point which is coming right now here itself. If you want to have a better results in a CFOA, we generally, not generally, we have to make sure that the values of the resistance are lying in few ohms only. Otherwise, it actually affects the internal resistance and the output. It doesn't work basically. So when you have 8844 or commercially available voltage feedback amplifier, we always use resistance in kilo ohms, etc. RF by R1. But that actually doesn't work in case of the CFL. So that is what we have observed. तो हम लोग का जो मेरा जो resistance का sweep था, I have never crossed 500 ohms. It was not giving the desired result. You can observe that in this particular case also. Now, interesting part, which again we found from various literatures, there are many authors have claimed that if you reduce the internal resistance Rx somehow, so if you reduce the internal resistance Rx, you can increase the gain further. So what we thought of, we had a kind of bias current. We should not be taking as showing as a bias current. We then renamed as a injection current. So we tried to inject a current at node X. What we are assuming here, if the current is going inside or maybe coming out, we can virtually say अगर current कम हो रहा है या sorry current अंदर जा रहा है बाहर आ रहा है, that means वो node का resistance अपने आप कम हो रहा है. That's kind of hypothesis. So that we can say that either ऐसा हो रहा है, then we can say that Rx reduce होता है, and Rx, if Rx gets reduced, the literature in the bandwidth current and gain relation says that bandwidth आपका बढ़ता है और gain भी बढ़ता है. Of course, it has some physical constant also. So this is what I have done. If you observe this graph, I'll show you the gradual graphs also. These are two end results. What do you mean by two end results? This was which I had already shown you in inverting amplifier. So without biasing current, I was getting a gain of around 12. But if I inject the current of 600 microampere or a bias current of minus 600, my gain shoots up to around 24. Same time, the bandwidth, the minus 3 dB bandwidth is also not getting affected. Ulta wo bhi बढ़ रहा है. So by injecting this particular current, surprisingly, what has happened that I was getting greater bandwidth as well as gain. So of course, in gradual cases, I tried increasing in steps of 100. So in the next graph, that would be clear. Yes. So these are the results for without bias, the pink one. The red one is for minus 100, then minus 200, minus 300, minus 400, 500. And then the last green is the 600. And then we found that if you cross more than 600, it again starts deteriorating. The mathematical model explain this is the same graph with the for publication purpose with the different dots, because you have to have a monochrome image. Blood cannot be accepted as a physical, I would say. When you take a printout, it's not properly visible. So this is the tabulation, the comparison for different bias currents. The gain is also different, the bandwidth is also different. The derivation of this is given in the same PPTs which if I click here, you can see the band, the derivation also. Or else at the end, after the thank you slide, I have appended this, the derivation of the relation, why this is happening like. If you observe after 600 microampere to 700, your gain is almost, I would say, slightly increasing, but your bandwidth decreasing. So up to this, I have explained that I have made a CFOA. I have also seen that you have something called as method of injection technique. Your bandwidth again increases up to certain level. Now coming to the last part, of course, which have most or many slides, but that would not take much of a time. Can somebody show me the time? The time is 5:59. Anyway, we have lots of time. Okay. Guys, any doubt till now? I'll take few doubt because ऐसा लग रहा है कि मैं अकेले बात कर रहा हूँ और आप लोग बैठे हैं. So अब तक कुछ डाउट है तो ले सकते हैं. Then I'll go ahead. If you have, you can write in the chat box. I think up till now I have received only one doubt. If no doubt, I'll drink water and continue. Manoj sir saying no doubt. Very good. दो डाउट का मतलब दो होता है, या तो सब समझा या तो कुछ भी नहीं समझा. Anyway, ये रिसर्च डोमेन है. It depends on the interest also. So right now, how many people are there? I'll just check in the chat box. Because at the start there were very less people. Hello. And I'll go to this part. Participants. Oh, there are 28. Not bad. Okay, I'll continue then. So coming to the final part of the presentation, of course, which is big one, the FS receiver, the major work, because this took me long time, as well as this took lots of blocks to be covered. So whatever you see on your screen on page slide number 52 is a general receiver block diagram, which you see in any so-called communication textbook. So you have received the FSK signal. मतलब मैंने whatever transmitter I had shown, the transmitter has transmitted the signal. Now I have a receiver. So FSK signal has been received. After receiving the FSK signal, you have to have two band pass filters. So that my constraint was first to design two band pass filter, one to remove the high frequency, other to remove the low frequency. In the conventional block diagram, as it is assumed all in the literature and the textbook like Wayne Thomasy or other books, that we had voltage signals. Maybe sine wave हम लोग दिए थे, sine wave, triangular wave. हम लोग ने assume ही किया था. Yeah, the authors have assumed that it is voltage. So if it is voltage, we used to use, or we have to use, called as envelope detector. Basically, what you mean by envelope detector is a precision rectifier. You have to have a full wave rectifier, and output of that is given to a comparator. So this is a non-coherent FSK demodulator generalized block diagram. But things changes when two things happens, because पहले BJT level पे काम कर रहे थे. अभी पहले तो BJT नहीं है. We are working with MOSFETs. And after MOSFETs also, if you're going for current receiver, आपका signal current है, तो even if the diode is a precision rectifier, वो diode on ही नहीं होगा. So I had constraints here. So anyway, I'll explain you one by one. So this is the general receiver block diagram. Okay. So I'll मैंने एक छोटा सा animation type बताया. It's not big deal. Observe. So first FSK transmitter output आया. That means आपका FSK signal आ गया, which has two frequencies, high low. मैंने जानबूझ के दो high और low में 1 megahertz और 3 kilohertz रखा है. So एक जगह पे 1 megahertz आएगा, एक जगह पे 3 kilohertz. So I need to have a band pass filter. After band pass filter, full wave rectifier circuit है. RC उसके बाद एक capacitor भी लगा है. That capacitor is basically they are acting as an envelope detector, and I have a subtractor. But this is assumed. If you see the heading, it's a voltage mode. If I show you the flow of the, देखो ये sine wave आया V15. Now just note down the I would say node name, because when I show you the waveform, बहुत लोग confused हो जाते हैं कौन सा waveform क्या है. So V15 is your input, which has low frequency. There are two band pass filters. So watching this, please. What I want you to do is, because otherwise हो जाओगे आप लोग भी. ये जो first है मैं एकदम आराम से बताऊंगा. For voltage mode FSK receiver. Then बाकी तीन वैसे ही है. Current mode के टाइम पे I need to explain you the part of current rectifier differently. Otherwise majorly things will not change. Of course आगे जाके current mode में change होगा, वो बाद में बताता हूँ. So I will be going very slow here. Otherwise there will be confusion. So V6A is a low frequency band pass filter output. मतलब 3 kilohertz का signal separate किया. 6B, V6B is a 1 megahertz हाई फ्रीक्वेंसी की है. देन इसको मैंने रेक्टिफाई किया. सो दोनों का रेक्टिफाइड, ये आ गया लो फ्रीक्वेंसी रेक्टिफाइड आउट, ये आ गया हाई फ्रीक्वेंसी. Then it's very easy for voltage mode. If you use a normal subtractor of LICD, ये कैपेसिटर का आउटपुट है, नॉर्मल सबट्रैक्टर यूज किया, received output at 6C. So number V15 input है, V6A, 6B band pass filter outputs है, VA1, VA2 are the outputs of the rectifier, and finally V6C you get the, this is for voltage mode. Fine. So I'll go ahead, but of course before we go for this, I have repeated this particular block again because पहला तो band pass filter में ही हम लोग मार खा रहे थे. So what we did, we have designed band pass filters for using different design methods, etc. Silent key filter helped us. So I'll just quickly go through few band pass filter. The starting ones are 8844 voltage mode band filter, and same I have replicated using the adjoint, and it worked as a current mode. So this is the circuit for band pass filter 8844. Iska frequency response. This is for 1 meg. You can clearly see the arrow showing 1 meg there. Okay. Then this was for meg 88442 megahertz. I'm just showing you frequency response. Now what I did, the same 8844 also have a property of working as a current mode. 8844 basically CF है, but luckily voltage mode करके भी act करता है. Yeah, it is the result. So using adjoint principles, using 44 similar values, I am designing for current mode. One thing which I have actually not highlighted here, guys, if you observe the frequency response 88444 voltage mode, observe the top. What I have is a gain of voltage. If you properly see here, this is the waveform taken from S.P.I.T. It is VTG gain. It's a voltage gain. Second is voltage gain. But after the 8844, if you observe the frequency response, clearly it's parameter current gain. So whatever you see here for 1 meg is gain. So 8844 current mode में मैंने band pass filter बनाया. Few more results. This is for meg. This is for 3.1, approximately 3 meg. But if you observe, this is the band pass filter using CFO. तो मैंने क्या CFO को replace किया. So I have not circuit वही है, सिर्फ उसको वो 84 से replace किया. So these are the results for different voltage mode, etc. So CFA current mode, this is for 3 megahertz. This is for 1 megahertz using CFA. Now, what constraint we had was we were trying for different frequencies, but many times for higher frequencies or sometimes for low frequencies, we were not getting the desired frequency response using normal silent key. So then we redesigned for few cases using new silent key filter. This was the latter part after what do you say, the annual progress seminar. Generally the suggestion comes, no, this is not working, try and do something like this. So we tried using new silent key filters. So we got few better results for 8844 because the target of ours was to design receiver using 8844 in both voltage mode, current mode, and using CFOA in both voltage mode, current mode, and compare the result. I repeat again, the target was using 8844, which is commercially available IC which works on 10 volts, make receiver using voltage mode and current mode. Then whatever device we have designed, that is our own current feedback operational amplifier, using that we have designed both receivers in current mode and voltage mode. So first target was to make perfect band pass filter. We have decided to test for 2 frequencies, 1 megahertz high frequency and 3 kilohertz lower frequency. So then we have 1 minute. We have successfully tried and tested for all the frequencies. As I said, these last two, we are not giving better results for the one for 8844, other for the CFI. So we have tried our best to redesign it for different cases. So the first constraint was the bandpass filter. So these are the few waveforms I have shown almost for all the frequencies which we have tried and tested. This is for CFOA 3 kilohertz. This is 1 megahertz current mode CFOA. Okay, so I'll come back to the complete receiver block diagram. Just excuse me for one moment. I need to get some water. Take a minute. Yeah, I have arrived. Thank you. Sorry. So I'll continue. So as I said, this is current receiver block diagram. I just demonstrated that what I have done. Guys, am I audible? Manoj sir?
Sir, audible, sir.
Okay, sorry. So deliberately, as there was a break in between that, I showed bandpass filter working. So I'll come back. So again, the same voltage mode receiver block diagram. Our target was first to design the bandpass filters. After bandpass, the full wave rectifier, which is normal one, or a precision rectifier. Then a capacitor for, I would say, acting as a filter, and then a subtractor. So FSK bandpass filter is separating high frequency, low frequency. Then you have rectifier out. Then normal pulse or square wave, and subtractor gives you the final. So this was a basic block diagram. But when it comes to complete block, what our target was, we need to do everything using single IC. So we have used model of 8844. So instead of showing this, I will show you this next part. Yeah. So this is the actual code written for, this is a schematic. We have actually put all the nodes and connected together. So I've used 1, 2, 3, 4, 5 8844, which are acting as a complete voltage mode receiver. If you people observe the first two vertically, I would highlight this way. This one is the bandpass filter, 6A output. This is the bandpass filter, 6B output. V15 is the input, which is a FSK transmit. This is VA1 output of the rectifier, VA2 output of the rectifier. And finally, you can clearly see this is a subtractor circuit giving you output VC. Sorry. In this waveform, everything is explained in one diagram, but slightly complicated, but still I'll try my best to explain this. I'll take time on this waveform because if I explain you this, it is very easy to understand the rest of the waveforms. Not only this case, because there are 3 more cases, because this is clearly, if you see the heading, guys, this is 88 voltage mode. It's a receiver 8844 in voltage mode. I'll go from bottom to top. Okay? So if you see the last waveform, V15 was the input frequency. Left hand side, this is a 3 kilohertz waveform. The right hand side, thick black, patch we can see. मैंने उसको zoom किया, zoom that. If you see the zoom effect on the right hand side, this is the 1 megahertz sine wave. What do I have? 3 kilohertz ka sine wave, and this is a megahertz ka sine wave. So including merging those, or I would say this is your FSK transmitted output. If you see the second graph is the output of the filter. So this particular case, this is V6A, the dotted ones. Right hand side patch is V6B. I've highlighted or I've zoomed 6B. So that's the that's the filter, bandpass filter output of 1 megahertz. Then the third is the output of the rectifier. So this is the output of the 3 kilohertz rectifier, and this is the output of 1 megahertz rectifier. 1 megahertz is very high frequency, तो मैंने इसको zoom करके यहाँ पे plot किया है. Amplitude of second case में थोड़ा कम हो रहा है, वहाँ पे gain का issue आ रहा था. So finally, after giving this is the main output. I would say ये input था, this was input, this was the filter output, this was rectifier. If this rectifier to the subtractor, finally I was getting this square wave. So there I was using a subtractor. Basically it acts as a comparator. So एक signal दूसरे से ऊपर रहेगा तो logic 1 देता है, नहीं तो logic 0 देता है, kind of thing. Same waveform. So next 3-4 waveforms are the same results. Explain for better understand. So these are two end results. V50 signal है, transmitted output. Transmitted output. This is the received signal, final square wave. Right? These are intermediate results. So if you observe 3 input है, यहाँ पे ये 1 megahertz बैंड पास फिल्टर नहीं, बैंड पास नहीं सर, ये 3 kilohertz का रेक्टिफायर है, ये 1 megahertz का रेक्टिफायर है, दिस इज 3 kilohertz का रेक्टिफायर आउटपुट है, and this is 1 megahertz का रेक्टिफायर. Final output waveform is square. So once this is done, आगे फटाफट जाता है, but this way I have explained you is 8844 just for clarity. मैंने अलग-अलग, sometimes I have kept it independent, sometimes I have overlapped it. Because when you actually publish the data, you can't have so many images. आपको एक ही image में सब कुछ होता है. Same graph for understanding. This is only megahertz. तो मैंने जानबूझ के सिर्फ 1 megahertz को plot किया है. It can be clearly visualized that yes, boss, the signal is of 1 megahertz. So if you take a scale and measure this is a 1 megahertz signal. I've mentioned the particular output which I'm showing. As I'm measuring 1 megahertz, 3 hertz, इसमें 3 kilohertz दिखता ही नहीं. Okay, so this was the first part. Now, everybody, the important part, the constraint which I had. If you see the heading, 8844 in current mode. Now, what I observed there, that whether it is 8844 or CFOA, when we have to have a rectifier, I was working with currents. So first we were unaware. We had directly used the normal same circuit of I would say CFA or 8844 based rectifier, but we found that output of rectifier was not coming as desired. In current, so what? उससे कम वाला currents which we are working were very less current, so that's why rectifier diodes were not getting on. So trend was to design current rectifier separately. So wherever you have current mode receiver, what we have replaced the voltage mode rectifier are by the current mode rectifier. So after doing lots of I would say literature survey, we found one particular literature where we have found the current rectifier. The reference number is given. Here we have 6 transistors. How it works is that they work in pair. So once you direct one, that is the current for one rectifier minus, that is negative half cycle comes, and otherwise positive half cycle comes, depending upon the gate voltage which is appearing at their gate voltage. Okay. If the current mode input signal, 1 minute, this header is, can you see this header? Or only I can see, I don't know. Okay, so if the current mode input signal is positive, N1 and N2 are off, while others are in saturation, input signal is transferred from M5, N6 and M3 to the transistor N4 in the same direction as I-rect plus, मतलब positive half cycle में जाता है, minus वाला जाएगा वो minus होके जाता है. So similarly, input signal is in negative cycle, transistor M3, M4, M M6 are off, while M1, M2 operate in saturation region. Accordingly, the signal can pass in the opposite direction from M2, that is rect minus. So this way, we obtain the result current rectifier. If you observe the current microamperes, so the above is IIN, that is the input signal, and the second below result is for IR1, that is the rectified output. Now the answer, I would say, result is more better visible if you overlap them. So your upper input and overlap them, so you can clearly see red lines are rectified outputs, not 100 proper, but with this we got the desired results. So using this, we have designed current mode 8844 block diagram using current rectifier. Now I'll not waste much of a time in waveform explanation. Of course, the node namings are different. Here IRXS is the input, IR11 and IR21 are the bandpass filter outputs. Current rectifier outputs are IRTR1 and IRTR2. Now one more important part which during the research we observed, in voltage we use subtractor or comparator. But in current mode, you have to actually subtract the currents. So subtracting current is different logic in case of MOSFETs or 8844 of CFOA. So we have, I would say, designed something called as CDBA, current differentiating buffer amplifier. The lots of literature is available. So using 8844 as well as in the latter part, we have used CFOA, which were acting as the so-called current differentiating. जैसे voltage का subtraction होता है वैसे current का subtractor को we call it as current differentiating buffer amplifier. Using those we got this result. Right now I'll explain only this graph because बहुत सारे graph अभी भी बाकी है. So the below one is the this is 3 kilohertz, this is 1 megahertz. I have zoom 1 megahertz. The ऊपर वाला उसका ऊपर वाला just second last I would say, that is the bandpass filter, 3 kilohertz, 1 megahertz. On top of that, you have 1 megahertz and 3 kilohertz rectified output using current rectifier. Finally, same graphs are been explained here separately. Individually, एक एक दिखाया मैंने. Separated waveforms. 8844 current mode. Separated graphs. Final to highlight that 1 megahertz is perfectly coming, which is overlap. As it is 1 megahertz, you can hardly see 3 kilohertz is a small line to 0. Now come to second part. So what I have explained up till now was making of the 8844 as voltage mode and current mode receiver. Now similar logic, I'll not time here. Now this is using CFOA. So everything was done on the same line as 8844. Only thing 44 replaced by CFOA, which was designed by us. So 8844 in circuit. This is bandpass filter 1, bandpass filter 2. Here voltage mode rectifier, full wave using precision, and finally you have a comparator circuit here. यहाँ पे हम लोग ने comparator use कर काम नहीं किया. Similar kinds of waveform, similar waveforms. Of course, waveform का results are different. यहाँ पे थोड़ा noise आया हमको. If I explain here from top to bottom, top one is the input waveform 3 kilohertz 1 megahertz. Then we have the bandpass filter outputs overlap. Then we have the rectified outputs. Finally, the output waveform. I have shown the zoom waveforms also here. Going ahead, independent separated clearly. This is 1 megahertz. Finally, the current mode. As I said, I've used the CDBA comparator use for CFOA. So using silent, I have used bandpass filter. So this is the last block diagram of a receiver using CFOA. So here the filters are separately designed using two CFOA. Then you have a current rectifier followed by a special filter. Basically, it's a CDV itself, current buffer amplifier. Waveforms, final waveform, input signal 3 kilohertz 1 mega. This is the band pass filter. This is the rectifier. यहाँ पे 3 kilohertz थोड़ा attenuate हो रहा है because of the not so effective band pass filter. But final output because of the comparator I am getting fine. So these are the all blocks as the topics. The implementing of communication circuits using current mode technique. Are independent waveforms shown here. The hand calculations are also done. So whatever I've got using the voltage mode and the current mode, they were verified for validation. Of course, done the hand calculations. So that PDF is also available. I would share that also with you. The complete derivation. So this way, for current mode, I have done the hand calculation using similar equations, and what I found that whatever I have calculations, the same were obtained using the simulation. Remaining part I'll not go in detail because it was for validation that when you are having a communication circuit, definitely you should be doing something called as bit error rate calculation. So I've done that in brief for 4 cases. I'll not go into this in detail right now. It is already almost 6:30. So this is the procedure. MATLAB and S.P.I.T in combination. You can add the AWG noise and the run in MATLAB. The output waveform is been given to the channel. It was received to the, and then the output square wave and square wave has been tested for few test results. And what I found here, or what we found here, is that still current mode is giving better bit error rate than the voltage mode. Okay, so I'm coming to the end of the presentation. The conclusion, whatever I have done or whatever I've shown in this particular presentation today, is implemented a new CFOA, done design, tested using current injection technique, which increases the gain as well as bandwidth. FSK transmitter compared for current mode as well as voltage mode. To do that, we have designed band pass filters, which are implemented for 2 typical frequencies for both current mode and voltage mode circuits. Current mode rectifier is designed for processing the filter output. Finally, in brief, the current mode and voltage mode FSK is designed using CFOA, which is our main contribution, and using 8844 and compared for power dissipation and bit error. That's it. I'm almost done here. These are the references. And after the references, as I said, S.P.I.T etc. was the person who we started doing it. I mentioned 1970. Actually, it is 1968. The first current conveyor new circuit building block was, I would say, was cited, was published. The data was published in 1968. There lots of work has been done on this. Thank you. After thank you slide, I have that, which actually shows you the design concept of the gain and bandwidth, that how the RX works. Anyway, I will not go into detail of this right now. definitely share this data. Thank you so much. Any doubts? Dr. Sir?
सर चैट बॉक्स
मुझे नहीं दिख रहा है 1 minute. Box. Yeah. Chat. I had shown, yes sir. Circuit, simulate this circuit is LT spice, yes, why not? You can do this in LT spice, but better than me, I think Rathod sir can answer it very well because he has done lots of hands-on in this semester on LT spice. Rathod sir, at the model files which are available in HSpice, LT spice, will it give the, I would say, similar result is doubtful. Rathod sir?
no, you can do it in LT Spice. Everything that you are demonstrating. You can import other model file also. That is also possible.
Yes. Thank you, sir. What are the other possible applications for CFOA? See, basically, let me tell you one thing. Once you make an op-amp has many applications, right from adder, subtractor, integrator, differentiator, even multiplier, etc. Everything, whatever you can think of, you can make by op-amp. Similar things can be done using CFOA. My experience, what I have seen in the literature, बहुत लोग से फिल्टर बना रहे हैं या फिल्टर पे ही बहुत काम हुआ है. फिल्टर पे लोगों ने IEEE ट्रांजैक्शंस निकाले. तो फ्रॉम माय पॉइंट ऑफ व्यू, जैसे ऑप-एम्प से सब कुछ बना सकते, CFOA से भी बना सकते, बट अल्टीमेटली व्हाट हैपेंस इज करंट से हमको ड्राइव करना है. So using current driving the whole circuit as we do in op-amp with voltage is many times not feasible. Yeah, वैसे waveforms output में नहीं मिलते. That is my answer. So times you will see work on sample and hold circuits, analog to digital conversion, digital to analog conversion ये होता है बहुत इफेक्टिवली. फिल्टर्स तो लोगों ने सब टाइप फिल्टर बनाया, मतलब जैसे हम लोग के पास एक यूनिवर्सल फिल्टर कंसेप्ट है ना. यूजिंग यूनिवर्सल फिल्टर यू कैन मेक लो पास, हाई पास, बैंड रिजेक्ट. तो यूजिंग CFOA 2 या 4 CFOA लगा के सब कुछ हो सकता है. सो मेजर वर्क using CFA, what I have seen in the literature, majorly filters, but ऐसे कुछ नहीं है. बहुत काम चल रहा है, बहुत सारे सर्किट बन रहे हैं. What else? Tools used for building CFA. What I've done using MOSFET circuit, जो मैं basic building block that using SPICE मैंने बनाया. Then I have actually also cadence पे भी मैंने काम करके I tried to replicate the same results. Unfortunately, cadence पे मुझे वो टाइप के वेवफॉर्म्स नहीं है, मतलब आउटपुट मुझे HSpice ने दिए वो मुझे cadence पे नहीं मिले. I discontinued using cadence, but you can start from scratch on cadence, so you definitely can do that. Anything else? Duality नहीं है. मनोज का एक क्वेश्चन है ना, I suppose. Is duality applicable to op-amp circuit? That's not called as duality. I'll repeat again. Okay, slide 18. Sir. See, the principle is applicable for circuits. In circuits also, I would say current, voltage, current, KVL, KCL, open circuit, short circuit. Duality, right? Capacitor replaced by inductor. Here we adjoint principle. So adjoint principle में we have to follow 3 things. Mirror image of the original circuit, input की जगह पे ground, output की जगह पे input and otherwise ground. That is called as adjoint principle. And that if you type adjoint principle, you get lots of literature using MOSFETs. Duality अलग है, reciprocity अलग है. So reciprocity we actually observe in 2-port networks. वो अलग है. Duality ही सर्किट थ्योरी में यूज होता है या BEE के बेसिक सर्किट्स में यूज होता है. एंड प्रिंसिपल वोल्टेज टू करंट मोड कन्वर्ट करना है तो यूज होता है. वो भी सब जगह एप्लीकेबल नहीं होता है, उसके लिए सर्किट हैज टू बी दैट काइंड ऑफ बैलेंस सर्किट. Yeah. One more question I can see. Does the CM technique provide good noise immunity as compared to AM technique? It's a question of debate. Good question. Actually, literature बोलता है कि करंट मोड में नॉइस का प्रॉब्लम होता है, बिकॉज करंट का सिग्नल बहुत वीक है ना, मतलब एम्पलीट्यूड इज लेस. Yeah, so voltage mode is better than current mode if you talk about noise immunity, because noise immunity ultimately has to go with the amplitude of the signal. I hope I have answered your question. Why application are the current-based circuits more advisable? Why don't have much knowledge whether they are actually using, but there are lots of IoT people around here and IoT regarding FDPs. We need to ask them the question. I am not the right person. I'll not be able to answer this question right now, but if anybody else there in the audience this can definitely answer, or I will definitely ask few of my seniors and get back to you before Saturday. Who's asking this? Manoj sir. Definitely I'll be there for the valedictory function, so I will try to get the answer of this by that time. Thank you so much. Who else? Thank you. Can we build digital logic using current mode? Of course, why not? We can do many things. Yes. See, basically this comes under the head of analog, but analog and digital goes hand in hand. So definitely yes. If you observe that current rectifier which I have used, or in fact मेरा जो output है ना, see मेरा पूरा receiver का output क्या है? 1 और 0 तो है. I am just generating a square wave. 1 0 for high and what do you say, low. 3 megahertz के लिए मैं 1 जनरेट कर रहा हूँ, 1 megahertz के लिए 0 जनरेट कर रहा हूँ. मेरा फाइनल आउटपुट रिसीवर का डिजिटल ही है. Of course, yes. Yes. PSRR and CMRR. Of course, this is a similar part which is definitely defined here also. Not thrown light on that because मैंने जो काम किया है ना वो under review है. So मैंने इसलिए इसको slides में डाला. Definitely. तो op-amp में applicable है, all the parameters, all the components or whatever we say characteristics are applied. Yes. Low power circuit. Somebody asked this question. Rutu Parekh, low power circuit. Yeah. Digital may you are saying low power. Of course, when we talk about current mode, the main objective of the current mode is to have low power. But low power, we also have a concept of problem of speed also. Luckily, current mode में नहीं होता, but there's a concept of power delay product. अगर आप सप्लाई कम करते हो तो आपका डिले बढ़ जाता है, and vice versa. एंड एनालॉग में ऐसे ही है कि अगर कुछ चीज अच्छी हो रही है तो डेफिनेटली किधर ना किधर दूसरी चीज खराब होती है. I have answered the question. Yeah. Answered, sir. Thank you. Sir, anything else? I hope I have made you understood this at least to 10%. Then it is my side. Sir.
Answer. Done? No, I'm waiting. For 1 minute, I'm waiting. If anybody has any question, they can again.
Yeah, I'm also waiting. So I just told you that. यहाँ पे डाउट कोई है तो पूछो. 7 बजे पहला क्वालिफायर चालू होने वाला है, DC वर्सेस मुंबई इंडियंस. टाइम है आपका 7 बजे तक टाइम है ना सर?
Yes, yes. No, I'm just waiting for any other question. I think that IoT question somebody has asked. Na, Ritu ma'am has asked, I suppose.
हाँ नहीं मनोज सर ने पूछा था शायद. मनोज सर ने पूछा.
Ritu madam has asked. IoT application.
Yeah, Ritu here. I asked because it is low power and then
correct.
Research happening in that field. So you know, I mean, we can do this kind of applications for especially for some specific IoT based application, we can develop such circuits. That's what I mean.
Yes, ma'am, you are right. You are absolutely right. That's what I wanted to add. You already said that. Because here you get a good gain. So therefore we can go for IoT applications, and low power is also possible. But then noise may create some issues. But then typical current mode circuit for a particular application can be designed for IoT application. Power is the main concern. No, low power. Power is the main concern. Sir, Bhagat sir will be able to comment. Sir, what about the, if you compare current mode and voltage mode, what about the power consumption?
Power in current mode definitely very less.
Okay.
Yeah, so it's always an optimized design, right? So we do trade off and then we get the optimized one,
Yes.
looking into power, noise, and all these factors.
But madam, at the same time, IoT may be require that what do you say, accurate kind of data in digital, right? So my answer was definitely IoT goes for low power. But if anybody is doing that in IoT, that is what I don't know. So definitely it can be tried.
To my knowledge, also not yet. People work on such, sub-threshold, low power circuits based on voltage only. So that research is much going on. So voltage mode circuits, but not with current mode, and that is what is an advantage here. So.
And that sub-threshold thing is majorly used in biomedical applications. Again, that sensors part. But of course, this is connected. That is indirectly connected to IoT only. Wherever you have signal and you are sending over the net, that is IoT. So definitely yes.
It should be looked into. Couple of good people in analog can come together and this can be worked on. Another thing, sir, have you fabricated any cheap, tape out? Have you done of such?
No, madam. No, ma'am, not possible. We tried that, but in India it is impossible. And
why? No. It is not impossible, sir. I just want to know that such good people. Interested people can come together. I am interested in such thing. So if you are looking forward, then I can get in touch with you.
Definitely, ma'am. I'll take your data. I will take your email ID, etc. Things, and we can talk offline.
We have cadence at our institute. So I am associate professor at Dhirubhai Ambani Institute here in Gandhinagar, and we have the simulation facility up to tape out. We can have it and develop a good application. Small, at least it can be a good start here in India for such IoT, and this is the future, right? So mobile applications, IoT, and all. So. In interconnect we have been working graphene interconnects and stuff, CNT, carbon nanotube graphene, where this current mode we have explored, and we have published many papers also, my group and myself. So
okay, no ma'am, what I can are you able to manufacture using CNT?
No, we have done this modeling and simulation of interconnects.
Okay.
Using this current mode technique.
Okay.
Because in voltage, the voltage drops, right? So as you said, the benefit of current mode and voltage mode. So.
Right. No, if that graphene thing can be done, because for me is one day work just to replace the CFOA model files from TSMC to CNT FET, and I can send you those files. If the manufacturing...
We can talk sometime later, sir. Yeah, because we have simple driver and receiver, so ours is, but the main part is the interconnect thing. So.
And definitely, as you are from Ambani's have lots of money, so they will definitely fund.
Here is not about money; it's all about knowledge, right?
Just joking.
No, you are right. But we say now that Saraswati brings Lakshmi, so maybe a good work.
Yeah, definitely, yes. We'll try and do that. Yes.
Yeah, nice talking to you, sir.
Because nowadays getting funds to the college is the main challenge what we have as a teacher.
Pardon? Yeah. What did you say, sir?
No, as a professor now, what we have been what do you say, given target is to get funds.
Yeah. But it has to be something, which makes application based and something, hardware kind of thing, which has a good application.
Professor Bhagat, you please take down the details of madam.
Yes, I'll take from file
And and tomorrow you start speaking, connecting to
No,
madam.
I'll talk to you first and then Bhagat sir. So we won't be involved.
Okay. Most welcome, ma'am. Most welcome.
Sir, photo लिया है क्या? I don't know.
Manisha madam.
Yes, sir. Thank you, Professor Bhagat, sir, for an enlightening and interactive, informative session. Sir has given us a good insights of implementation of common mode techniques for the communication circuits. I hope all the participants now well aware about the all common mode techniques and the how can they implement the circuits using this SPI.T and all the cadence softwares. So thank you, sir, for this encouraging session.
Thank you, madam. Thank you so much.
So thank you very much, everybody. Thank you, sir. So we are going to meet tomorrow morning. Tomorrow morning we will have a session 10 o'clock. Dr. Sudhakar Mande will be here, and we'll start again on time. Okay. And tomorrow evening again 5 to 7, Dr. Naushad will be there as usual. Okay. Thank you very much.
Thank you all. Thank you so much.
Thanks. Bhagat sir.
बोलिए sir.
There is another link for CWC this thing meeting. Shall we meet on that?
Right now?
2 मिनट के लिए.
हाँ. यहाँ पे आप लोग चले जाएंगे ना.